All right, let's dive into one of the weirdest but most important theories in all of science, quantum physics. It's the rule book for basically everything, from what's happening inside the sun to how the chip in your phone works. And yeah, it has a reputation for being intimidating, but I promise you, the main idea behind it is something we can all get our heads around.
Okay, but first, a little warning from one of the absolute giants of the field, the brilliant Richard Feynman. He famously said, "If you think you understand quantum physics, you don't understand quantum physics." Which, yeah, that doesn't exactly make you feel confident, does it? Right? You hear that and you think, great, if a Nobel Prize winner who helped build the theory says he's confused, what hope is there for the rest of us? It's a totally fair question. But here's the secret. That whole idea that quantum physics is just fundamentally impossible to understand, it's really kind of a myth. Because even though some parts are, deeply strange, on a practical level, we actually understand it incredibly well. In fact, you could argue it's the single most successful scientific theory in all of history. I mean, this isn't just a bunch of abstract equations on a chalkboard. It is the engine that powers our entire modern world. We're talking computers, lasers, nuclear power plants, the whole shebang. You don't get those things from a theory you don't understand. We know it works. The real question is, what's the one big idea that makes it all hang together? Well, the key to unlocking quantum mechanics, the one thing you really need to grasp, is a single, central, and totally radical idea. It's a complete break from how we're used to seeing the world, and it applies to absolutely everything on the tiny, tiny scales. See, in the normal, everyday world, we picture an electron as a tiny little particle, right? Like a microscopic billiard ball. But quantum physics comes along and says, nope, that's wrong. Instead, an electron, and everything else for that matter, is actually described by a kind of abstract wave, something called a wave function. Now, this is super important. This is not a physical wave, like a ripple in a pond. It's a mathematical wave, a wave of probability. It tells you where an electron is likely to be, but it never, ever tells you with 100% certainty where it is. And this isn't because our tools aren't good enough. This fuzziness is baked into the very fabric of the universe. It's a feature, not a bug. So, how do we get from this blurry cloud of possibilities to the solid little particle we can actually detect in an experiment? Well, it's kind of like a three-step process. First, you have the wave function, which is spread out and contains all the potential places the particle could be. Second, we make a measurement. We poke it, we look at it, we interact with it somehow. And third, in that exact instant, a single, definite particle just pops into existence at one specific spot. And this right here, this brings us to the single, biggest, most profound mystery in all of physics. It's the part Feynman was really talking about in that quote. It's called the measurement problem. Physicists have a name for what happens when that spread-out wave of possibilities snaps into a single, real particle. They say the act of measuring it collapses the wave function. And here is the billion-dollar question. How? Why does the simple act of looking at something fundamentally change its reality? What is so special about a measurement that it forces the universe to pick just one outcome out of all the possibilities? The completely honest answer is, we don't know. Nobody knows. This is a huge gaping hole in our understanding of reality. The best way to see this in action is the famous double-slit experiment. It's awesome. If you shoot something like paintballs through two vertical slits, you get what you'd expect, two lines of paint on the wall behind them. Simple. But if you shoot electrons, even just one at a time, you get this wild, multi-band interference pattern. Now that pattern is something only waves can make, which means, and this is the mind-bending part, each individual electron must be acting like a wave, going through both slits at the same time and then interfering with itself. So that's the bottom line. An electron behaves like a spread-out wave when nobody's watching, allowing it to do impossible things like being two places at once. But the instant you try to measure it, the moment it hits that detector screen, bam, it becomes a single particle in a single spot. This is it, the core idea, particle-wave duality. Okay, so once you accept this fundamental idea that everything is a wave until you look at it, a whole bunch of other super weird but totally logical consequences just fall right out of the math. Let's look at a few of them. First up is superposition. Now, this sounds really complex, but it's not. It's just a fancy term for adding waves together. Think about dropping two pebbles into a pond. The ripples overlap and create a new, more complex pattern. Well, for a quantum particle, this means its wave can be a combination of multiple different states. It can be, in a very real sense, spinning clockwise and counterclockwise at the same time, until you measure it. Then you've got entanglement. This is what happens when two of these quantum waves interact in just the right way and become described by a single, shared wavefunction. From that moment on, they are linked, forever. If you measure one of them over here and find it spinning up, you know instantly that its partner is spinning down, even if that partner is on the other side of the galaxy. Einstein hated this idea, but experiment after experiment has proven it's real. And then there's this wild one, quantum tunneling. Because a particle is really a fuzzy wave of probability, the edges of that wave can actually leak through a solid barrier. This means there's a tiny but non-zero chance that the particle can just appear on the other side without ever breaking through the wall. And this isn't just some weird party trick. It's literally how the sun works. Without quantum tunneling, the protons in the sun's core couldn't get close enough to fuse. No tunneling, no sunshine, no us. So it might all sound like total chaos, right? A universe made of fuzzy waves of probability. But it's not. The quantum world is still governed by very strict, very fundamental rules. Probably the most famous of these rules is the Heisenberg uncertainty principle. So let's go back to our wave. If you have a nice, long, perfect wave, you know its wavelength, and therefore its momentum exactly. But because the wave is so spread out, you have absolutely no idea where the particle is. Now, to know its position precisely, you have to squeeze that wave down into a single sharp spike. But a sharp spike is a messy combination of countless different wavelengths, so now you have no idea what its momentum is. You can know one or the other, but never both at the same time. It's a fundamental trade-off. And finally, where does the word quantum even come from? Well, it comes from the word quanta, which just means a packet or a discrete chunk of something. Think of a guitar string. When you pluck it, it can only vibrate at specific frequencies, right? It makes an A or a B or a C. It can't make a note that's in between two notes. Its vibrations are constrained. An electron's wave in an atom is the same deal. It's trapped, so it can only exist at specific, discrete energy levels. Energy comes in these little packets. It is quantized. Whoa, okay, that was a whirlwind tour of a very, very weird place. So let's just take a breath and boil this all down one more time to the absolute core concepts. So let's put it all together. At the very bottom of reality, everything is described by a wave function, a wave of possibilities. This naturally leads to the strange truth of particle-wave duality. For some reason we don't understand, the act of measurement collapses that wave into a single reality. And the fact that things are waves allows for bizarre but real effects like superposition and entanglement, all governed by a fundamental built-in uncertainty. If you've got those ideas, you have a really solid handle on quantum physics. And so we kind of end up right back where we started. On the one hand, quantum mechanics is the most powerful, most precise, most successful theory humanity has ever created. But on the other hand, it has these giant philosophical mysteries, like the measurement problem, sitting right at its heart. We can use it to build our entire technological world with stunning accuracy. But the reality it describes is so alien, so counterintuitive, it leaves us with this final, lingering question. Will our brains, which evolved to throw rocks and find berries in the classical world, ever be able to truly, intuitively comprehend the quantum one? Thanks for joining me.